Digital twins, a methodology for digitally optimizing energy consumption in buildings. This is a PhD research project at the Centre for Smart Modern Construction, Western Sydney University, Australia. It is well established in the literature that the buildings account for 20% of the total energy consumption in Australia. It is worth mentioning that most of this consumption results from the interactions between the building and its occupants. Researchers and industry practitioners have resulted to embracing technologies to address energy consumption buildings. However, most of these technological applications have been directed towards the provision of monitoring and alarm capabilities, and does not efficient help in optimizing buildings' energy consumption. Additionally, these technologies have been geared towards buildings which have limited occupant building engagements and also implementations in lab-based environments. To be able to adequately optimize buildings' energy consumption, there is the need to consider the dynamic nature of buildings resulting from their interactions with occupants. A technology capable of capturing the dynamic nature of zero-F buildings and providing access to real-time data to efficiently optimize buildings' energy consumption is the concept of digital twins, DTs. DTs are connected and synchronized digital replicas of physical assets, which continually updates using several data sources. They can be simulated for real-time prediction of current and future conditions of assets. This study, therefore, aims to optimize energy consumption and indoor environmental parameters, that is, thermal, lighting, and air quality for occupants' dynamic building usage, using the Internet of Things devices such as sensors and digital twin technology. A university library located at the Kingswood campus of Western Sydney University in Australia is used as the case study for implementing the digital twin technology in this study. To demonstrate the prototype of the DT system, the user must select the floor to display the targeted group study room. The user then clicks and show the visualization tool, that is, Tego VIZ, under the add-ins ribbon to visualize the real-time and historical data of the parameters being monitored. After the floor and visualization tool have been selected, the user specifies the room and number of data points to visualize, the specific group study room and the number of data points to be visualized. For instance, 1,000 points have to be entered in the QTY section. The user has to click on the Get button to download and view the results. Based on the displayed results, the user would have to specify the date and time to display. This allows the user to ascertain the indoor environmental conditions in the selected group study room. At this stage, the user can right-click on the displayed results interface and select Zoom to Fit Data tab to access the results of the specified date and time. These results can then inform decision-making regarding the current and future conditions of the specific room. The data retrieved can then be compared with established recommended standards for the various monitored parameters for efficient decision-making regarding comfort and energy consumption in the building. In conclusion, this study has provided an efficient methodology for optimizing energy consumption and indoor conditions in buildings using real-life data. It has also implemented the concept of DTs to simulate buildings' indoor conditions. Finally, the study developed best guidelines for optimizing energy consumption in buildings. This research intends to explore data analytics techniques and integrate them into the developed digital twin system to provide feedback to the building management system, that is, the BMS and actuators, to take corrective actions in the physical library building. It is also envisaged that an extension of the research would provide the facility managers with an opportunity to access the monitored data via their mobile devices, that is, cell phones.